Hello, everyone. Thank you for joining me in this webinar. And this is going to be fun, at least I hope so, because what I'm going to be talking today is how you commit crimes against code, how you generate code that you look at and make you want to cry and rage and just go ballistic. As an aside, we're also going to cover why you would want to write something like that. I think that I've been trying to cover this concept for the past 20, 15 years. And before I go into that, I have to say a disclaimer. I care about performance, like a lot. I build a database for a living, and performance is one of the primary things that you have that makes a difference. So if I can get better performance out of some practice or some tricky things, I would absolutely do that. I would remind you all about the inverse square in Quake code, which is, I have no one understand how people got to that. But what I would like to share with you today is some of the secret techniques that allow you to get far higher performance from your system. And let's look at that. Before we look at that, and this is the real disclaimer, code quality matters. And just to give you some context, I've been working on RavenDB for about 15 years. Some of the code dates back 20 years ago, which means that it really matters that we are able to take the code, make sense out of that, maintain that over decades, years, and team members that have been with us and left and came back and all much of other stuff like that. If I'm looking at my Git repository right now, I have people that I last spoke to them in 2010, whose code still work. And I might have to go into that code base and fix something. So maintainability is absolutely mandatory because it is very easy to accumulate technical debt to the point where it's unsustainable. But at the same time, performance. I mean, come on. So how do you get good performance? It's very easy. You summon a demon from the pits of hell and you sacrifice something important to it, usually your code quality, in order to get good performance. And the typical jokes that we make in the office is, okay, I wrote that. Now I need you to take this code and make it ugly. Also fast, but mostly ugly. Let's see what is actually involved in doing this. So I want to make it faster, and let's make a deal with the devil. Here is probably the simplest scenario you can think of. We have a JSON array that contains a whole bunch of commands. And we need to parse that and operate on that. This is an example I took from our documentation. And this is real RavenDB code. I mean, RavenDB needs to process something like that. And if you think about it, stop for a second. This is not complicated. This is not hard. This is a day-to-day task for you. How would you build something like that? I asked ChatGPT to write the code. And it did something like this. So you read the J object from the body, and then you just iterate over that, and you can see that we're using a switch here to do something with the commands. Now, this is perfectly fine code. In fact, this is easy to read, easy to understand, and for most people, that's all you care about. RavenDB is not most people's. And that's actually a problem. Let's explain how many things are bad in this piece of code from RavenDB perspective. Well, you can see here that I'm going to materialize the entire JSON into .NET objects. What happens if I have a large list of commands? Well, I'm going to have a large number of objects, managed objects, which the GC would then need to collect. One of the things that we care about in high-performance systems is reducing allocations because that reduces the cost of GC. So that's problem number one. Problem number two, look here. I'm generating a new string here. For that matter, look at the number of string accesses that I have. So this would return a string. This would return a new string. So this is a lot of allocations galore. Now, we also have to look at this one. You see all of those cases? What happened behind the scenes? Well, the compiler is going to inject some if statements. So this is actually really expensive from our perspective. But we can do better. We have to throw away a lot of convenience, but we can do better. Here are the issues. Again, we may have large number of data, lots of strings, etc. Now, in here you can see 2 property names. In reality, I have 25. So that's quite a lot of items that you have to go through each one at a time. There is also another aspect here. We care about high performance. Try to imagine that this piece of code is invoked 500,000 times a second. What happens? It's going to generate a whole bunch of garbage. And then the GC is going to run and stop the world. And you're going to have super fast, boom. And it's not working at all. This is super common in high performance. By the way, high performance, not the numbers that are given here. 500,000 per second. This is what we are trying to achieve on a sustained basis. If you're dealing with a few hundreds, low thousands, don't even bother. It doesn't really matter. So the first rule of thumb, the first thing that we want to do is not allocate any .NET objects. And in order to do that, we actually had to write our own JSON parser, which operates over the bytes instead of materializing data into a string. And this is amazing because that means that we were able to reduce the number of allocations that we have. What's the output of a JSON parser? Well, a JSON object. That's quite obviously the case, no? However, in our case, we are not, that's the problem because we're talking about a complex object. If we have a really complex object, what happens? Lots of items for the GC to collect. That's a no-no. We don't want that. So instead, we are actually going to generate our own native format directly into native memory and create something we call a blittable JSON object, which is basically just a way to format a JSON object so you don't have to have multiple .NET managed objects around that, which means that I don't have any GC costs. But one of the key aspects of JSON is that you deal a lot with strings. So what happens now? Well, we are dealing with the strings. We actually implemented our own string class specifically to reduce the number of allocations that we have, because the entire thing is sitting on top of some native memory, which means that now we have the ability to map it directly from the disk using memory map files, which means that now we have zero copy. So we started from this little tidbit. Oh, I need to parse some JSON. And we ended up with our own JSON parser and our own format in native memory to describe a JSON object. This allows us to store the data in a memory map file, and that leads to 0 copies, which is an incredible achievement because one aspect of the design managed to cover so many aspects that were really troubling for us. But this is just step number 1. There are more. So now we have the JSON object in native memory. We need to figure out how to detect which command this is. I don't want to materialize a string. So I have a way to get a property name, which is just a byte pointer and the length of the property name. What sort of code would I write now? Well, it's going to be something like this. So in here, you can see something really fun. This is actually using a feature of the JIT where it detects this sort of pattern, and instead of calling this method and allocating a new byte array each and every time this is called, this is actually going to go ahead and give you a constant value. In fact, accessing this property is going to be erased by the JIT. It's just going to point it directly to the raw data in the constants table, which means that now we are able to write code like this. And this is fun. This is easy. This is quite readable. It's effectively what we used to have with the switch statement, but this is still problematic. Remember that I have 25 property names. How many comparisons am I going to have here? Well, at worst case, 25, 26. But this is actually worse. Look at this. I'm doing a comparison on bytes, which means that I have to compare 1 byte at a time, which can be incredibly expensive. And yet, well, what can you do? I mean, I have to compare strings, and you compare string by basically comparing the contents. Thankfully, I don't care about case sensitivity. I am case sensitive, not case insensitive, so I don't have to translate that. That drastically simplify my life. So what happens now? Well, I'm going to make the code ugly. Take a deep breath, and behold, even the daemon is confused by this sort of thing. Take a moment, look at the code. This is how we detect that this is a put. It has a length of 3, and there are some magic numbers here. And more magic numbers here. What? What? Just what? So here are these magic numbers. And let's see what happens. So if I convert this number to bytes, I'm going to get these bytes. So remember, this is int32, so it's composed of 4 bytes, and I basically decompose them here. And this is a short, so 2 bytes, and decompose here. And now you can see what are the ASCII values of those values. So delete, delete. So what is this code about? What is it doing? What's going on? Well, think about it. Look at this line. I'm casting the buffer to an int and comparing it to this constant. I'm casting the buffer plus 4 bytes to a short and compare it to this constant. And we know that those are the ASCII of delete and TE. So what actually happens is that I can do in 2 machine instructions, compare this whole thing, compare it to known values. And this is important because instead of using memcompare or sequence equals or something like that, which have to go of all of the bytes and have an OM operations, I have just 2 operations, compare in, compare short, and then you're done. It's a whole different way of thinking about that. Once you realize that what's going on, oh yeah, I can do that. But you end up with code like this. And that's hardly readable. So this was a problem. But before we get there, I want to talk about another aspect. So far, I only talk about this, but there's also this. Previously, with the if after if after if, I would have to make 25 comparisons. Using this model, I'm comparing only the values that have the same length. So this small detail has a huge impact on the number of operations that we make. And then we reduce it from sequence equals to comparing the raw values. And this is how it went for a very, very, very long time. There was no better way of doing that. But that sucked. I mean, that's, as you can imagine, that's not very readable code. Recently, .NET added the ability to have UTF-8 constants. You can see it like this. And that means that now we have a better way of actually dealing with that because this is constant. Why does it mean that this is constant? Because it means that we can get the JIT to cooperate with us. So what about this thing? What is this compare constant call? Well, let's take a look. Here is the compare constant call. And notice that this is being aggressively inlined. What we are actually telling the system is this. I'm going to be calling this with a constant. So the JIT, when it compiled this, knows what those values are. And now I'm going to say, okay, here is the constant reference. And I'm going to be using this one. Let's say that I'm running on an x86 machine, x64 machine. So now I'm calling you with the reference, the pointer that I'm comparing us against, and the length that I have. Which leads to this code. Notice that this too is set up to be aggressively inline. And look what we have here. Size at this point is a constant value. What is the JIT, the just-in-time compiler, going to do when it encounter a known constant value? It's going to do something called pruning. Oh, I know that the size in this case is 3. I know that because this is a constant value. The constant compare constant was inline, so I know it's still constant. And this is also constant, so now I know this is 3. So this is also a constant value, so I can remove that. I can resolve this using at compilation time. And all of these really messy things end up with something like this. So now you compare to the constant reference and to the byte, which is effectively what we do here. In terms of machine code, this has tremendous number of operations, as you can see. But we were able to structure it in such a way that this and this are going to generate the same output. But as you can imagine, this is so much nicer to read and operate, to understand. It does have an impact in terms of maintainability of the system. We are relying on the compare constant being optimized by the JIT. This is a fairly safe assumption to do, but we actually have to write checks that will verify this is the case. In some cases, there is just no way of escaping writing code like this. But this is so much better. We actually went ahead and changed this piece of code to this very recently in the last few weeks. And it's interesting that we did that. We did that not because we had to. That piece of code did not change for a very long time. Well, that makes sense. Would you want to change something like that? So by making this refactoring, changing this, we made the code a lot easier to modify and extend. Now, let's talk about another interesting aspect, which has horrifying implications. I'm going to write some JSON. What's the cost of doing that? You might think that, oh, generating strings, writing to the network buffer or something like that, but no. The most expensive part in writing JSON is write escape string, which is utterly, ridiculously, stupendously insane. Why would this be so expensive? 50% of the runtime of writing JSON we spend in this method. Well, what is it actually doing? It's taking a string which may contain escape characters like new line, quote, stuff like that, and writing that as an escaped string. In order to do that, it has to scan the entire string. And the code implementation, or when I actually ran this test, was that it did that one character at a time. As you can imagine, that's the definition of ouch. So I already mentioned that we actually have our own string implementation. We call it lazy string value. And one of the primary reasons it exists is specifically because of this profiler output. Because what we need to do, we need to be able to write the details out, the string out, in as efficient manner as possible. And what we end up doing is computing the escape structure during write time. When we write a document, we compute all of the escape characters, and we write it as number of escape sequences, and then we have an array of the number of escape sequences, and then we have the raw string text. And the reason this matters is that in most cases, we don't have any escape sequences. So we're able to take the entire raw string bytes and throw them directly into the output with as little cost as possible, which leads to another interesting observation. You think I need to write to the network, but that's not something that I actually want to do. I want to send as much data as possible to the network, so it would use the bigger packets, would give better opportunity to do compression, a whole bunch of reasons. So we actually have multiple layers of buffering. Let's look at write string as a good example. Here we have the lazy string, and you can see there is some conditions. This is where it's getting interesting. So here is the number of escape sequences. And this is if I have a very long string, I don't care. This is the optimized portion. If we don't have any escape sequences, I can just call write raw string. And you can see something really interesting here. If I have enough space here, I ensure that I have enough space, copy the raw data, and then I'm out. Otherwise, I may have to do this in multiple times and call flush. Flush is interesting because it takes the buffer and write it to a stream. But this stream is actually typically a memory stream. And the reason for that is that I typically, as you can see, this is writing a single document. So I would be writing one document and then flash it to the network and then move on, or at certain sizes or something like that. The whole point is that the local buffer is there to make sure that I can allocate. I have a big enough buffer for most operations almost immediately. And I don't have to check, oh, do I have enough space? Okay, write a value. Do I have enough space now, etc. I can just assume that I have enough values and operate like that. And then I write it to a memory stream. And then from memory stream, I batch a big write and write it to the network. Okay, now take a little bit of time and look at this code. It's nasty. Let's try to understand what this is doing. Again, you can see the use of aggressive inline. And this is really, really weird. This is an extension method on bool. But this means that we're actually taking a reference to the parameter, casting that to a byte, accessing the value, and getting that as an int. What? What this actually does is something very simple. If value is true, it's going to return 1. If value is 0, value is false, it's going to return 0. So what? Why do we care about something like that? Well, we care because we can do this. We can do this without using a branch. Let's look at the code. Here is where we're using something like that. So if the size is less than 30, return the size. This is okay. If the size is greater than 256, we are supposed to return size plus 2. Otherwise, we return size plus 1. But here's the assembly. And I'm assuming that you have some familiarity with C#, probably not a lot of familiarity with assembly. Let's see what's going on here. We are comparing the value that we got, which is in ECX register, to this value, which is 30. If this is greater or equal than 30, we jump to here. Otherwise, we're just returning that. We'll say we are moving from the input register ECX to the output register of EAX and returning that. Now, we are zeroing EAX and comparing ECX. So now ECX is the size to 256 in hex. And now we're doing something interesting. What's going on here? Saying set greater to AL, which is basically, there is complexity here because it's actually using different levels of the same register. But what is important is that set AL to 1 if the comparison is greater. And then I'm just adding to that. Let's see how this looks like if I have a more normal piece of code. So you can see here, this does the exact same thing. If this is large, do a conditional and get this or this. But now you can see something really interesting. We have additional 2 instructions. What is worse, those are called jumped instructions or branches. Remember, this code isn't for you, it's for the CPU. And there is an issue here. When you jump, the CPU doesn't necessarily know whatever the jump is true or false. So it has to wait or speculate what this value is going to be. With this approach, there is no speculation, there is no jump. You reduce the amount of work that the CPU has to do. And that has actual measurable impact. Now, so far I've shown you just a little bit of code. What I would like to show you now is a lot of code. Let's look at I'm sorry, I have to make sure that I'm in the right branch. And I'm using examples taken from RavenDB. And those are actual things that we're doing. This is okay. So just to give you some context, this is 16,721 lines. And this is what the code looks like. I don't know if you're noticing, I'm scrolling up. This is one method that I'm going through. What is this? What's going on? Well, the answer is quite simple. This is a whole bunch of code that is meant to translate, to do integer compression. Specifically, this does SIMD bit packing. It takes a list of numbers, an array of numbers, and compact them into lesser bits. And the reason it is so long is that we actually generate specialized implementations. Here's when I need to store 30 bits per value in the input. Here I'm using this to store 29 bits per item in the input. And the whole idea here is that I'm able to do in one shot a compaction of 256 numbers in a really efficient way. This translates to over a kilobyte of machine instructions just to process one batch. But this is optimized to the nth degree. You can look at this in the, you can look into that in the assembly output. 0 branches. Only SIMD operations. SIMD stands for single instruction, multiple data, which means that we are able to process that really, really rapidly. To give you some context, when I'm running this, I can compress in the order of 600,000 numbers per second on one core. And I can decompress. I'm sorry, I made a big mistake. I can compress bits, but I compress numbers at a rate of 600 million, not 1,000, 600 million numbers per core per second. And it can decompress at a rate of 1 billion per second. Now, you may look at this code blind or scream and cry, but you know what the really, really scary thing here is? This is still not optimized. We haven't made it ugly yet. There are probably still performance left on the table. We will pursue that and make this code uglier and faster. Now, here's another interesting aspect. So we can do specializations using generics. So we have a class, a lookup, which takes a key. And the key has a bunch of methods. And look at how I'm specifying the generic constraints on the lookup class. It must be a struct, and it must implement a lookup key. This is a pattern that we are using in many different ways, because think about what the JIT does when it sees this. It is always going to see lookup specialize to one of those things. And this is a struct. So it knows everything, what is this size, that there are no overriding and things like that. Which means that what it basically does, it takes the code and does a complete specialization of that. So I can do inlining across this and all bunch of other things like that. If you're familiar with C++, this is the nearest you can get in C# to get template specialization. We actually get to the point where we are doing comp time operations. Let me show you what I mean. And look at this method. What am I actually doing here? This is really interesting because this is known at compilation time. So if you call this method and the key is A64 lookup key, the JIT is going to say, oh, I know this is never going to be the case, and erase that. And if I'm calling that with double lookup key, then this is the only code that is going to be generated for this method. Which means that I have this really beautiful way of generating the appropriate values easily and cheaply. Now, this is like the kiddies pool. Let me show you how far we've pushed this. Take a minute, look into that. This is C# code. It's not Rust. It looks a lot like Rust code, but it's not Rust. And all of this means that I have a way of generating a delegate that is specialized across all of those. When I'm actually calling that, I'm going to call an implementation that has been generated specifically for that. This is not a pattern or an approach that we should use globally. But this is how we implement sorting, something that we expect to be called billions of times per second. Absolutely worth it for the additional complexity. Entirely insane, but absolutely worth it for the overall behavior. We have a question here whatever casting takes up CPU cycle or extra instructions? The answer is no, but I'm going to show you how you can figure it out. There is this lovely website, and it can translate C# code into assembly. So I'm going to do it like this. If type of okay. Now you can see this. And now I'm going to tell this, hey, I want you to generate specialized version of this for this and this. So here is the version for int. It doesn't, let's do it for long. Here's the version for this. Zero code. But I can do better. Let's assume convert to long. And I'm going to do something like this. So now, if this is the long, sorry, convert to int, sorry. If this is an int, we can just return that. If this is, let's say, long, something like this. Notice what we have here. I have a whole bunch of code and casting and a whole bunch of other stuff like that. Here's the version for int. Well, just return that. Here's the version for long, which, as you can see, is really, really nice. There is no casting, nothing whatsoever. By the way, if you look at the decompilation here, you can see it does just the right thing. When you move to the assembler, this way you see it. But in general, look at things this way, it looks much better. Now you can see exactly what's going on. So here we're saying shift it to the right by 32, which is hex of 20x. 20 hex is 32 decimal, and write it to the appropriate location, the EX output. Easy and cheap. You don't need to worry about any of that. Okay, so let's look at this one. I already mentioned that we took ownership of memory by moving allocations to native code. That also allows us to have our own allocators. Arena allocators allows us to not actually think about releasing memory because I have a well-defined scope of work. If I need to process a request, the request may allocate memory, which is fine. And go ahead and do that. But I'm not releasing anything. And by the time the request ends, I can just drop all of the memory in one shot. It greatly simplifies the amount of work that they have to do. It means that the GC is blind and not going to have to pay for that down the line. I still, and this is the fun part, I can still draft the GC to watch my back. Oh, I forgot to release that, then the finalizer will kick in. But for the most part, doesn't really happen. I also want to show you what do I mean by single instruction multiple data. This is when we have vectorized operations. So you can see what's going on. I created a vector of 256, which contain 8 integers. Here's another one. And now I can add them together, resulting in this. This little line of code is one instruction operating 8 items at a time. As you can imagine, that's a lot faster than one at a time. This is the basic of how the how this works. Well, using, in this case, you can see that I'm shifting 8 numbers by 29 in one shot, one instruction. Okay. Something that's important to understand is that when you're improving your performance, every small change that you make compounds. So you add 1% here, you remove 1% here, you optimize by 2% here, you save an allocation, and at the end of the day, this is 1% of 2% and 3%, and you end up with a significant amount of improvement. Surprisingly so. And with that, I hope I haven't scared you too much. I would be very happy if you have any questions that you'd like me to answer. Okay. Let's see. So the question, hopefully you can see that, about what did they use to generate the SIMD file. This is here we go. So this is actually code that has been converted, the entire thing converted from work done by Daniel Amir. And this is my conversion of his script that generates C#. I basically convert all of that. I actually have a whole series that discusses this. I'm going to edit here so you can see that. Basically discuss how I did that, what's happened, what is the impact of that, those sort of things. Okay, moving on. Can you optimize code too much and end up preventing the compiler from doing some of its own optimizations? Absolutely. So the one absolute rule of performance optimizations is that you have to measure. More than that, you have to know how to measure. Just to give you some context, we have a set of benchmarks here. Some of them are measuring stuff that is, like here, all of the experiments that we made. Here, like tremendous level of effort that we put into making sure that the changes that we are making are actually viable. In the most part, you end up with rough understanding of what's going on, especially because, as you can see, we are looking at what the compiler is doing, reading the assembly instructions. So that gives us a good indication of what's going on. But even if you can read the assembly, you still need to be able to verify that this actually ends up being faster. by specializing code, you also have more code. We take that into consideration. And the answer is yes, absolutely. For the most part, this is an absolutely acceptable trade-off. It used to be the case that 1 megabyte download was insane. The RavenDB code base is the zip file, something like 70, 80 megabytes, something like that. And that also includes the entire .NET framework because we ship it inside our own code. Additional code at this level is really not that meaningful. And another aspect is that RavenDB is meant to be server software. So something that is going to be running for a very long period of time. The additional cost of more code is absolutely worth it. Okay, that is great. If you have any more questions, feel free to go to RavenDB and go to the discussions. We would absolutely love to hear from you and hear what's going on. And I hope that you enjoyed that. Thank you very much and have a great evening, morning, whatever is going on in your end. Bye-bye.